Hi, this is Team 21050 presenting the ROIP, a device that rapidly images physiological processes on the second-to-minute time frame. Our sponsor was Dr. Urs Utzinger from the University of Arizona's Department of Biomedical Engineering. The team consists of myself, Shannon McCoy, Dominique Galvez, Mohamed Al-Azimi, Mohamed Al-Haddad, and Benjamin Carpenter. Our presentation will cover the background of the ROIP, the requirements that the ROIP must fulfill, and then the various subsystems of the ROIP and how they accomplish the goals of this project. So here's Ben to give us a little bit of background.
Thanks, Shannon. Like mentioned before, the ROIP images physiological processes and movements of hemoglobin, biliverdin, and hemosiderin. Currently, there are no devices on the market that can provide this type of simultaneous analysis. The success of the ROIP could assist in biomedical research involving skin-level processes and might eventually lead to improvement in patient care when this technology is integrated into non-invasive imaging devices. The goal of this project was to develop a portable, non-invasive skin imaging system that captures at least 250 frames per second in order to observe physiological processes, like blood flow or sweat production, in a time frame varying from a few seconds to 1 minute. Here's Dominique to explain further.
Thanks, Ben. So how will the ROIP accomplish this goal? Well, since we want to excite many different kinds of biomarkers, 14 different wavelengths were selected that can excite these biomarkers. As the ROIP collects image frames, the LED wavelength that's being used will swap, resulting in a rotating ring of LEDs. Therefore, as the camera takes images, each frame will be lit by a different wavelength of light, highlighting a specific biomarker. In this way, the user will be able to almost simultaneously observe changes in multiple biomarkers over relatively long periods of time. This may lead to further discoveries linking biomarker behavior to skin-level processes like blood flow that may give more information about skin-level features. Now back to Ben for some project requirements.
In addition to a few general limitations like size, weight, and portability, the system needs to fulfill some additional requirements. It must be able to acquire and save images at a rate of at least 250 frames per second. From half a meter away from the test subject, it must have a resolution of 600 microns or better. For each frame, the illuminating LED pair must illuminate the target as uniformly as possible, with a signal-to-noise ratio of 2 or better. Also, the system must be able to operate for up to 1 continuous minute without compromising the structural integrity of the 3D printed casing, overheating the electronic components past their optimal operating temperature, or overloading the image-gathering computer. The system must also turn itself off automatically after 1 continuous minute of image acquisition.
To create the ROIP, the project was split into 5 subsystems: optics, illumination, software, power, and the outer casing. The optics subsystem consists of carefully selected off-the-shelf parts. Since we are using such a wide range of wavelengths, the camera and lens were chosen due to their respective wide sensitivity and wide transmission spectra. Together, they are able to effectively image an object half a meter away with a resolution of 540 microns, successfully fulfilling the system's resolution requirement. For the next subsystem, I'll pass it off to Shannon.
The illumination system consists of 26 LEDs and all the components needed to run these LEDs. The team worked with the sponsor and a graduate student working under the sponsor to complete 2 custom printed circuit boards, one for the LEDs and one for the circuitry to drive the LEDs. These circuits were specifically designed to efficiently switch on and off the appropriate LEDs in sync with the shutter of the camera. This synchronization was accomplished with a microcontroller. The microcontroller receives an output signal from the camera, signaling that a picture is about to be taken. With this input, the microcontroller then picks 2 of the LEDs and switches them on for the duration of the picture. Altogether, this synchronization of the circuitry with the camera allows us to take over 500 light wavelength isolated frames per second. The LEDs chosen for our project are high power and dissipate a considerable amount of heat. The heat generated by the circuitry was modeled extensively during the project's development, and in order to prevent any damage to the system that could be caused by this heat, the team designed an aluminum heatsink that effectively pulls heat away from the 2 PCBs and expels it into the system's surroundings.
The software subsystem needed to do 2 things for ROIP: run the camera and run the LEDs. The software needed by the camera was written in Python and would initialize the settings on the camera, acquire images, and save the images. To efficiently save the image frames at over 500 frames per second, a queue system was devised, wherein the software would loop until it gathered 14 frames and only then it would save. With this configuration, the software was able to acquire, display, and save the images without overstraining the computer's resources. The software needed to run the LEDs was a microcontroller code written in the Arduino language. After uploading onto the microcontroller, it takes the shutter signal from the camera and switches to the next pair of LEDs. With these two software components, the ROIP has been proven to swap LEDs and acquire and store images in a time-effective manner.
The ROIP is powered through a standard 120-volt AC US wall outlet. The power subsystem first converts the AC power from the wall into DC power. Next, it steps down the voltage in order to provide appropriate amounts of power to the LED pairs, drivers, and microcontroller. This DC to DC voltage step-down was accomplished with adjustable DC to DC step-down power converters, also known as buck converters. In fact, we were able to reduce the amount of buck converters needed from the expected 15 to just 7.
Lastly, the casing subsystem was designed to effectively support the other components of the total system. The only requirement of it was to be able to carry the weight of the system without failing or suffering any structural weakness due to any heat generated by the system. Both of these requirements were successfully tested upon the completion of subassembly integration.
Finally, with all subsystems integrated together, we have the ROIP. In addition to some of the testing mentioned for each subsystem, there were requirements of the system as a whole, including interfaces and total runtime.
Here is the complete system. The complete system allows us to take wavelength-isolated photos to zone in on specific biomarkers and track them over time. One example would be tracking blood flow within bruises. By observing how much blood flows through the bruise, or the alternative paths it may take, researchers may be able to conclude information about the bruise itself, such as its age. With the completed ROIP, the sponsor will be able to explore skin-related biomedical research that may lead to future medical devices. Thank you for your time, and we look forward to answering any questions you may have.